Copyright in these lectures is either owned by the ANU or a third party who has licensed the ANU to use it. Students may use the recording for personal study only. No lecture may be communicated online, copied or shared without the prior permission of the ANU.
Okay, let's start today's lecture. And firstly, still welcome to today's lecture. And I understand that because Tuesday's lecture starts very early at 8, so it's really hard to get here at this very early time. And firstly, some announcement. First is about the quiz. So basically, the quiz will close tomorrow at 11 a.m. And even though the quiz is only worth 0%, but it is compulsory. So I strongly recommend you to finish the quiz before the deadline. And it is really important to get your feedback during the first half of the semester. And also, I think some of you have already finished the quiz, so you will see I have already attached very detailed comments for each of the questions. And also, obviously, after the quiz, you will immediately get your answer. So in that case, you can get your feedback immediately. So if you have any questions about the quiz, please prepare your questions, and then in the next week's tutorial, the tutor will talk about the quiz. So if you have any questions for the quiz, please prepare it and then ask your tutor about it. So that's about the quiz. And also, another thing is about the questions during this course. I think we have already spent 4 weeks in talking about everything. So I think for now, I think you should have a lot of questions. But unfortunately, I'm really sorry that due to the large number of enrollment, you are strongly encouraged to ask questions during consultation hours and discussion forum. So actually, I think your first option is actually to ask your questions directly during my lectures. For instance, you can ask me now, so any questions for this course, for the previous lectures. So usually when I ask any questions, usually I will not receive any response. So if you have any questions, I think your first option is just to ask me directly during the lectures, because you can really benefit. I think everyone can benefit from it. So that's your first choice. Your second choice is just to ask me during my consultation hours. I think the consultation hours are right after today's lecture from 10 to 12. And usually face-to-face communication is better than answering your questions especially during emails. So if you have any questions, welcome to my consultation hours, and I'm really happy to help you. And your third choice is just to if you really do not have time at these consultation hours, you can actually go to any of the consultation hours for all the 5 tutors. So that's your third choice. And also you have fourth choice. You can, if you really do not have time during these 2 hours and also during these 5 hours, you can reserve by using email, by reserve any time to, not any time, but available time to meet me in my office. So I can give you additional consultation hours if you really do not have time during these 7 hours of consultation, I think, for me and also for my tutors. So that's your fourth choice. And the fifth choice is just to ask questions directly on the discussion forum. So you do have a lot of chance in this course to ask questions. So sorry about the large number of enrollment, but I really cannot control it. It's due to the program. So in this case, just my suggestion is to just ask questions if you can, by using the above 5 different methods. So that's just my suggestions. So any questions about this course, about everything? So I'm really happy to help you during my consultation hours, because I think usually the most efficient way for me to give you feedback is to answer your questions during your consultation hours. And firstly, let's continue the previous topic. So for the previous topic, we are talking about the inferential tools. So for the inferential tools, I think this topic is very similar to the topic in simple linear regression model. And I mentioned the very big difference here. So basically there are 2 differences. The first one is the notation is much more involved for multiple linear regression model, because we have multiple explanatory variables. So that's the first difference. The second difference here is, even though we have very similar t-test, but the interpretation or the explanation of the t-test is different. And also we have a new test, which is called f-test. So that's the main 2 differences. But when we consider the t-test, I think you will find that everything is very similar here. So the only difference for the t-test is the distribution. So the distribution here is t distribution with the number of the degree of freedom n minus k minus 1. But it's still consistent with the simple linear regression model case, because for simple linear regression model case, we have k equals to 1 because we only have 1 explanatory variable, and the number of the degree of freedom equals to n minus 2. So that's n minus 1 equals to n minus 2. So that's the difference. So by using this difference, we even if for the t-test, so in the t-test we want to test beta j equals to 0, and j is just 1. Beta j is just 1 of the coefficient. So remember our multiple linear regression model: y given x equals to beta 0 plus beta 1 x1 plus so on and so forth plus beta k xk. So you can test any of the coefficient. Any one of the coefficient equals to 0, so that's the t-test. And the idea for the hypothesis testing is exactly the same compared to the simple linear regression model case. And then we can propose almost the same test statistics, but because the sampling distribution here is a little bit different, with a little bit different number of degrees of freedom, so here we need to compare this test statistics to the t distribution with the number of the degree of freedom n minus k minus 1. So this is the only difference. We just compare a slightly different distribution. But the computation of the p-value and also how can we use this test to get our conclusion is exactly the same. So that's about t-test. Any questions? So the only difference is the distribution. So in order to help you understand it by using R output, so I just give you the R output directly. So one thing I want to mention here is that in your final exam, I think I will not ask you or require you to write down any R codes. Please remember that. But you do need to understand the R code and also R output. So what's the meaning here? For instance, in this example, if I give you these R codes and also R output, you actually need to understand them. But I will not ask you to write any R codes in your final exam. So I think I have explained a lot about the output in this summary table. You can consider it as a table. So we have talked about, we have the estimation, we have the least square estimation. So firstly, based on this R code, by using this LM function fit, so what can we know from here? So we can know we are actually here fitting this regression. Mu y x1, x2, x3 equals to beta 0 plus beta 1, x1 plus beta 2, x2 plus beta 3, x3. So you need to translate the R code into something you are familiar with. So basically, this R code just means that we are fitting this regression line. And in order to get the fitting of this regression line, we need to have the least squares estimation for the parameters. So how can we find the least squares estimation? So the least squares estimation is here. So that's beta 0 hat, beta 1 hat, beta 2 hat, and beta 3 hat. And correspondingly, we have the standard error. So the standard error is the standard error is the standard error of the corresponding estimate. For instance, we have the standard error of beta 3 hat here, which equals to 0.94. And also we have the t-value. So what's the t-value? T-value is actually the test statistics of t-test. So what's the test statistic, if you remember? So this is the test statistic. So the test statistic here just equals to beta 3 hat divided by the standard error of the beta 3 hat. So I think there is a question in quiz which is about it, but under the simple linear regression model case. So the t-value is the test statistic of the t-test. And the last one is the p-value, the corresponding p-value. So I think firstly you need to understand this. You can consider it as the coefficients table, and this table is really important. It includes the estimate standard error, test statistic of t-test, and also the p-value of the t-test. So by using this p-value of the t-test, we can, for instance, we can get this conclusion from this p-value that beta 2 is significantly different from 0, because we reject the null hypothesis with this p-value smaller than 10 to the power of minus 15. So this means 7.7 times 10 to the power of minus 15. So it's smaller than 0.05. So that means beta 2 is significant, or beta 2 is significantly different from 0. And also in this table, I think in the simple linear regression model part, we have also mentioned something here. So this number, this residual standard error, so what's this? It's the estimation of sigma. So it's sigma hat. So what's sigma? If you remember, sigma, this is the sigma hat. And what's sigma? Sigma is actually from our constant variance assumption. It's the variance of the random error, or it's the variance of the response variable. So here in this table, we have the sigma here. And also we have the number of the degree of freedom. So this is the corresponding number of the degree of freedom. So that means that's n minus k minus 1. And what is k? So you can find the k here. So just count how many variables here, because we have 3, so k equals to 3. So in this case, you can use this n minus k minus 1 to get how many observations here, how many observations in total for this regression. So here we should have n equals to 96 plus k plus 1 just equals to 100. So that means our sample size is 100. So I think by using this output, you can actually get a lot of information. That's really important in this course. I think for now, I focus on these coefficients and also this row. And I will talk about the other part, like the multiple R squared, and also the later part, I think in my later lectures. So when I explain the R output, please be very careful about it. Any questions? Okay. So we have mentioned that by using this R output, we know that in this R output, we are actually fitting this regression line. So by using these 3 explanatory variables, x1, x2, and x3. So we have already explained the t-test result for the beta 2. However, we also can have the t-test result for beta 1. So this is the t-test for beta 1. And also this is the t-test for beta 3. So we can find those are the p-values. These 2 p-values are larger than 0.05. So in that case, we can consider that this hypothesis testing for beta j equals to 0, j equals to 1, and 3, they are not significant. So they are not significant just means that we cannot reject beta j equals to 0. So if you have a look at the model, if beta 1 equals to 0, so that means we do not have this term. So that means in this model there is no x1. But in this case, can we say that because we have these 2 insignificant results, can we say that both x1 and x3 are not needed in the model? The answer is definitely no. Please remember that. I think I give this reason here. You can consider this reason as the explanation of t-test beta 1 equals to 0 versus beta 1 is not equal to 0 for multiple linear regression model. So the explanation for the t-test or the interpretation of the t-test for the multiple linear regression model is totally different from the interpretation of the simple linear regression model. So please remember that. So what's the explanation or what's the interpretation? This is really important here. So the test of beta 1 just tells whether x1 is needed in the model that already contains x2 and x3. So that means when we test beta 1 equals to 0 and beta 1 is not equal to 0, we implicitly consider that the model has already contains x2 and x3, and then we test whether or not, in this case, x1 is needed. So in this case, this test only considers whether or not x1 offers any information over and above that of x2 and x3. So that's the meaning for this test. So in this case, when we have this result like the beta 1 is not significant, what we can only say here is that when we already have x2 and x3 in the model, maybe x1 does not offer extra information. So that's really important to see this interpretation. This is actually from the, if you remember, the interpretation of the coefficient for multiple linear regression model. It is from the interpretation of beta 1. So if you remember, what's the interpretation of beta 1? So for the interpretation of beta 1 is actually the increase of the mean of response when x1 is increased by 1 unit, but we need to control x2 and x3. So if you compare these two, the meaning, the explanation of the t-test and also the interpretation of beta 1, we both have this control x2 and x3, or we have this, the model has already contains x2 and x3. So it's actually from here, from the interpretation of the multiple linear regression model. So in this case, you need to be very careful when you look at the t-test result. And also, that means whether or not beta 1 is coefficient. So whether or not beta 1 is coefficient, the beta 1 is significant. Whether or not beta 1 is significant depends on what other variables have been included in the regression. So you need to be very careful about this t-test. And in order to explain more about this idea, so let's just look at these two different models. For instance, for the first model, we eliminate x3, and for the second model, we eliminate x1. So let's first look at the regression result here. So this is the model we remove x3. So if x3 is not included in the model, so what will happen in this case? So by using this output, we can find that now beta 1 is significant. So this confirms our conclusion here. Whether or not beta 1 is significant depends on what other variables have been included. So if we do not include x3, in this case, we actually have the significant, you can consider it as the significant beta 1. And similarly, for x3, we also have the significant beta 3, because the variable x1 is not included. So based on this conclusion, we can have this roughly impression that at least one of x1 and x3 is actually needed in the model, because if we try to eliminate one variable, we always have this significant result for the corresponding coefficient. So that's our doubt. But for now, we do not have any tool to test this kind of guess. So how can we do that? So in order to do that, firstly, we need to propose a new test. So what's the new test? The new test here is that we want to test whether or not at least one of the two variables is needed in the model. And the opposite here is none of the variables are needed in the model. So that's what we want to test. But for now, we actually have no tool to accomplish this kind of complicated test. But in order to simplify this test, simplify those words, we can consider to use some notations. So none of the x1 and x3 is needed in the model. So what's the meaning for it? It just means beta 1 equals to beta 3 equals to 0. Because if you write down the multiple linear regression model, you will find that if beta 1 and beta 3 are equal to 0, so in that case, that just means these two variables are not needed in the model. And similarly, you can translate this sentence into this word. So that just means at least one of beta 1 and beta 3 is not 0. So that's our new test and our new target here. We want to find some tool to test this kind of beta 3 equals to beta 1 equals to beta 3 equals to 0. So that's our f-test. So what's f-test? F-test is used to test whether or not several regression coefficients, like beta 1 and beta 3, in the multiple linear regression model are all zeros. So I think the important thing is just to compare it to the t-test. What's the difference between this test and the t-test? So for the t-test, we can only test one coefficient equal to 0. We cannot test several coefficients are equal to 0. So this is the difference. So we have already talked about the incentive to perform this kind of several coefficients equal to 0 test. We call it f-test. And also we compare it to the t-test because it's something new. We have, for the t-test, we can only test one coefficient. And that's the start of the f-test. And so far, any questions about f-test? You need to know the reason why we consider the f-test, and also you need to know the difference between the f-test and also the t-test. Any questions? Okay, if you do not have any question, then we can continue to propose the test statistic and also the distribution of the test statistic for this f-test, because it's something new. So we do have totally different method to construct the test, test the statistic. So because it's different from the t-test, so the test statistic is constructed differently. So in order to construct the test statistic, we introduce some important terminologies in the multiple linear regression model. And here, basically, we just introduce this terminology, which is called sum of squared error. So for this sum of the squared error, so what's the definition of it? So basically, for sum of the squared error, firstly, we can compute the residual. So the residual is just the difference of the real y and also the fitted y. And then we just square those residuals and then add them together. So we can treat it as the sum of the squared error. It's literally as its name, the sum of the squared error. And also sometimes we can call sum of the squared error, we can use another name. So basically you can treat deviance just as a new name of the sum of the squared error. So sometimes we call it sum of the squared error and sometimes we call it deviance. So the reason why we can also call it deviance, I think mostly in this course, is that we can use this deviance function to compute the sum of the squared error in R. I think mostly in this course, that's the reason. But actually, deviance has a lot of very important meaning, I think, in statistics. So if you are interested, you can just check it online. So what's the meaning for deviance in statistics? But in this course, basically, you can just treat, especially for multiple linear regression model, you can treat deviance equivalent to the sum of the squared error. So because of the definition, the sum of the squared error, so this is the sum of the squared error, obviously this measure can be used to capture the goodness of fit for the multiple linear regression model because it's an error. So if this error is small, so that just means that the fitting is good. It's basically based on the definition. It's the sum of the squared error. If the error is small, then the fitting of the model is good. So it can be used to measure the goodness of fit for the multiple linear regression model. So how can we use R to compute the sum of the squared error, SSE? So what you can do here is just you actually have two different methods to compute. The first method is just to use this definition, the sum of the squared error, the sum of the squared error. So inside is the residual. So basically the residual is the difference between the real y and the fitted y, which is exactly the error. Or you can just use the deviance function directly. And inside the deviance function, you should have this LM function result. You should put in the LM function result. So that's the definition for the sum of the squared error, and also that's the definition for the deviance. Any questions? Okay, after we have talked about the sum of the squared error, which is a measure to capture the goodness of fit for the multiple linear regression model. So in this case, we are going to use the sum of the squared error of different multiple linear regression models to construct the test statistics of F-test. So how can we construct it? So firstly, we need to transform the F-test here. So this is exactly our F-test into different models. For instance, if we have beta 1 equals to beta 3 equals to 0, so that means we actually remove this x1 term and also x3 term. So that means here, the H0, the null hypothesis, is equivalent to this model is appropriate. This model is the model without two variables, x1 and x3. Because it has less variables, so we call it reduced model. So the H0 can be translated into this, the reduced model is appropriate. So correspondingly, for the alternative hypothesis, we have this full model with all the explanatory variables. So that means if we want to test this F-test, we actually test which model is better. The reduced model is better or the full model is better. So that's the idea. So in order to test this reduced model is better or the full model is better, firstly, we need to prepare some quantities which are going to be used in the test statistic. And the first one is that the number of the coefficients being tested is really important. And here, because we only test beta 1 and beta 3, so D equals to 2. And also, if you consider this idea to compare two different models, to compare reduced model or the full model, you can also consider D is the difference between the number of the coefficients in the full model and also the number of the coefficients in the reduced model. So that's the meaning for D. D is really important. And another one is really important here is the number of the coefficients in the full model. So that's k plus 1. So in our case, because we have 3 variables, k equals to 3, so k plus 1 equals to 4. So that's the number of the coefficients in the full model. So if we know the number of the coefficients in the full model, and also we know D, so we also know the number of the coefficients. So the number of coefficients in the reduced model is K plus 1 minus D, because the difference is D. So that's some quantities we need to prepare. So the next thing here is to prepare the sum of the squared error or the deviance for the full model, and also the sum of the squared error for the reduced model, and also the sigma hat for the full model. So if you forget about sigma hat, you can have a look at it. So what's sigma hat? So this is the sigma hat. And if you still remember the definition of the sum of the squared error, so that's exactly equal to the sum of the squared error divided by the number of the degree of freedom. So here, we only need to compute the sigma hat for the full model. So that means we only need to compute the sigma hat based on the fitting of the all explanatory variables, x1, x2, and x3. So we need to prepare these quantities. And also we have this kind of relationship. So this relationship is really important. You can verify that we always have this satisfied. So that is the sum of the squared error for the full model is always smaller or equal to the sum of the squared error of the reduced model. So that means for the reduced model, we have less variables. And for the full model, we have more variables. So that means if we add variables in the multiple linear regression model, we always have a better fitting. So that's the property of the least squares estimation. And basically, it's a mathematical result, but I think understanding it is not hard, because from intuition, if we have more information, obviously we should have a better fitting for the model. So now our target is just to compare the different two models. We want to compare the reduced model and also the full model. So the idea here is that if the reduced model is appropriate, then we should have this result that the fitting for the reduced model and also the fitting for the full model should be very similar. Because the reduced model here, the reduced model y given x2 equals to beta 0 plus beta 2 x2, and the full model here, mu y given x1, x2, x3 equals to beta 0 plus beta 1 x1 plus beta 2 x2 plus beta 3 x3. So if this model is better, then the fitting of these two should be very similar. So that means this sum of the squared error should be very similar. The reason here is that if this reduced model is better, the full model, because the full model contains the reduced model, so the reduced model here, the reduced model is a special case of the full model by letting beta 1 equals to beta 3 equals to 0. So that means if the reduced model is better, so in this case, we should have very similar fitting for this reduced model and also the full model. Then the difference should be very small. If the difference is very small, so that just means that we almost have no difference for the non-hypothesis and also for the alternative hypothesis. So that means we cannot reject the non-hypothesis. So that's the idea to construct the test statistic. To compute this extra sum of squares, basically to compare the fitting of the reduced model and also the fitting of the full model. And correspondingly, because sum of the squared error has another name, which is called deviance, so we can also call this drop in deviance. So we can call this extra sum of squares, or we can call it the drop in deviance. So we are going to use this quantity to help us construct the test statistic. So the real test statistic here is, firstly, consider the comparison between the two models. So this is the difference between reduced model and the full model. So that's in the numerator part. And also we need to consider the number of the coefficients being tested, if you still remember. So in our case, d equals to 2, because we are only testing beta 1 equals to beta 3 equals to 0. And remember that, I think if you still remember the test statistic in the t-test, we always need to consider the denominator for the reason that we need to consider the randomness of the numerator. So we need to consider the variation of the numerator into our test statistic. So that's the reason why we consider this denominator being the sigma hat square full. You can consider it as the standardization. So intuitively, if this test statistic is small, so if test statistic is small, that just means no difference. No difference between H0 and HA. So in this case, we should not reject H0. So that's from our intuition. But actually, in real practice, we actually need to have some standard to help us to make this decision. So how can we do that? We need to compare this test statistic to the F distribution. So what's F distribution? And I will explain it later. But in order to determine the F distribution, we need to determine two numbers in the F distribution. So those are also called the number of the degree of freedom for the F distribution. So how do those numbers come from? So the first number, D, is actually from the numerator, if you remember. And the second number, n minus k minus 1, is from the sigma hat full. So what's sigma hat full? When I review the sigma hat, what's the sigma hat, I actually give you the formula. So the sigma hat full square equals to SSE full divided by D, divided by n minus k minus 1. So the other number, n minus k minus 1, is from the denominator. So in this case, we have the distribution and also we have the test statistic. So we can compute the p-value. So this is the formula to compute the p-value. So if the p-value is smaller than alpha, so that can imply the test statistic Ts is large. And if test statistic is large, so there is a huge difference between H0 and HA. So in this case, we should reject H0. So that's the logic for the F-test. I think it's a little bit more difficult compared to the t-test, but the idea is the same. So basically, we just want to compare the difference between the null hypothesis and also the alternative hypothesis. And that's the F-test. And one thing I need to talk about is this F distribution. So here I just give you a F distribution. If I remember, this is the F distribution of F246. So you can see for this F distribution, firstly, it's the histogram of the F distribution, or you can consider it as the density of the F distribution. Secondly, you can see for the F distribution, we always have the positive value. So it starts from 0, so that means it's always positive. It's different from the normal distribution. And also another very important feature is the skewness. So the F distribution is skewed. It's not symmetric, it's skewed. So by using this distribution, we can actually compute the p-value. So the p-value, so how can we compute the p-value? The p-value is just the F distribution, the probability that one F distribution is larger than the test statistic. So if you can compute the test statistic here, for instance, where is our test statistic? So if you happen to compute your test statistic here, so this is the value of your test statistic, then the p-value should be here. So that is the probability that this F distribution is larger than test statistic. So that's your p-value. So you can compute your p-value by using this F distribution. And if this p-value is smaller than 0.05, you can get this conclusion that test statistics is too large, and you have a huge difference between H0 and HA, and in that case, you should reject H0. So that's the way for us to perform the F test. Any questions? So I think the most important thing here is just to know we have a totally different test. So we always need to know that when we have a different target, we should have different methods to deal with this target. And when we deal with this target, we are using some concept which is called sum of the squared error. And this measure can help us capture the goodness of fit for the multiple linear regression model. So the idea for the F-test is just to compare the goodness of fit for the reduced model and also the full model. So if the goodness of fit for these two models are totally different, so in this case, we should prefer this full model because the full model is more general. So let's look at some special cases for the F-test. And the first one is just called the test of overall significance. So that means we want to test all the coefficients except for the intercept. So why we want to test this? So basically, if we have the null hypothesis, so corresponding to the null hypothesis, you need to always translate this null hypothesis into the modeling. So if you have this null hypothesis, what's our reduced model? So the reduced model here is mu y given x equals to beta 0. So there is no x1, no x2, or no x3. So that means we do not need x at all in this case. So all the x variables are not helpful for us to predict y. So that's the reason why we need to consider this test. Because in this case, we can actually get this conclusion that whether or not we need explanatory variable in the model. So, and because this test is really special and also is actually very important, so in the summary output, we actually have the result for this test, and I will explain it later in the R example and R output. But remember that we have this test which is called testing of the overall significance. And the second special case is to test only one coefficient. Because F-test can be used to test several coefficients, and one coefficient is the special case of the f-test. So in this case, by using the f-test, we can still accomplish the same thing compared to the t-test, but the test statistic is different, and also the distribution is different. So here, for the test statistic, we should have this formula to compute the test statistic, but because it's a special case of the f-test, we have the d equals to 1, because we only test one coefficient. And also, here we still have the f distribution with these two degrees of freedoms. So I think usually in your final exam, I will ask you to get the test statistic from the table or from the output, or and then I may ask you this question: what kind of distribution you should compare to when you consider this test statistic? So what you need to answer here is just to answer what's the distribution, the f distribution, and also you need to answer two numbers of the degrees of freedom. You cannot answer one, because for f distribution you need to have this two to define an f distribution. So you need to answer these two numbers of degree of freedom. And because it's a special case, and also it is testing exactly the same compared to the t-test. So in this case, it's equivalent to t-test, but we have a slightly different test statistic. Because we are targeting the same thing, so we should have the same result, otherwise something is wrong. So in this case, you will find that they do return the same p-values by using these two different testing methods. And also I will show it by using the R example later. And also this test statistic, under this very special situation, this test statistics is going to be used for the sequential variable selection in our topic 9. So I will talk about how to use this test statistic for the variable selection. So these two special cases of the f-test are very important. And also the f-test itself is also very important. So I think basically we have finished the hypothesis testing part, I think, for the multiple linear regression model. And I think in the next half of today's lecture, I will talk about confidence intervals and prediction intervals. So please just take 10 minutes break, and then we are going to continue today's lecture. Okay, let's start the second half of today's lecture. Firstly, any questions about, basically I think in the previous lecture is about F-test. Any questions? Okay, then let's just talk about something you should be more familiar. So that's the confidence interval and prediction interval. So I think for the confidence interval and prediction interval, I think you can find more similarities compared to the simple linear regression model case. So for instance, if we look at the confidence interval for beta j hat, so what we need to do is just to consider this practical sampling distribution, and the only difference is the number of the degree of freedom in the T distribution. And by using this result, we can directly obtain the 1 minus alpha confidence interval for beta j. So this is the 1 minus alpha confidence interval for beta j. It just equals to beta j hat minus plus the T quantile here times the standard error, and I have already given the standard error. So what's the T quantile? So the T quantile here is just the quantile of the T distribution with the number of the degree of freedom n minus k minus 1. So if you still remember the simple linear regression model case, so this is the only difference. So in the simple linear regression model case, we have explained the T quantile for the number of the degree of freedom 2. So here we should have the very similar results. So what's the T quantile? So firstly, you can just draw a T distribution. So consider this T n minus k minus 1 distribution. And then what you can do here is just to find the quantile. So if you can have a look at this T distribution, if the probability on the right side here is 1 minus alpha divided by 2, and the probability on the left side here is on the right side is alpha divided by 2, and on the left side is 1 minus alpha divided by 2. So in this case, we can call this 1 minus alpha divided by 2 quantile, and then we just give get the value here, which is T n minus k minus 1 alpha divided by 2. So that's this 1 minus alpha divided by 2 quantile for the T n minus k minus 1 distribution, very similar to the case for the simple linear regression model. And by using this formula, you can actually obtain the confidence interval. So how can we obtain the confidence interval? So if you still remember the table, so by using the our output, by using this coefficients table, you actually know the estimation beta 3 hat, and also you know the standard error beta 3 hat. Standard error of beta 3 hat. So the confidence interval here for beta 3, so by using this output, the confidence interval of beta 3 should equal to beta 3 hat minus plus the T n minus k minus 1 alpha divided by 2 quantile times the standard error of beta 3 hat. And also, what's n minus k minus 1, if you still remember? So that's the number of the degree of freedom for the T distribution. So we have this number of the degree of freedom here. You need to check this table. And you can find that this n minus k minus 1 here equals to 96. And by using this table, you can know the value of beta 3 hat, and also you can know the value of the standard error. So usually, we consider alpha equals to 0.05. So that means you need to know the T quantile N96, and this is 0.02. to 5, you need to find this t quantile. So how can you obtain this t quantile? You can just use R to get this quantile directly. So I will show you how to use R to get this quantile. But I think the more important thing is just to know the number of the degree of freedom from the table, and also to know the estimation and also the standard error from the table. But for the quantile, so how can we obtain the quantile? You do not need to check any table. I think even if in the other courses you should check the table to get the quantile. But in this course, what you need to do here is just to use R, packages. We do not need to use any package. We just use R directly. So how can we get the quantile if you still remember 96.025? So what you can do here is just to use this Qt function. So if you do not understand the Qt function, just question mark Qt, and then you can find this Qt. So what's the meaning for Qt? Firstly, you can input the vector of probabilities here. This is the first argument. And then you need to input the number of the degree of freedom. And here, you do not need to consider the other part. So you can ignore those parts. So let's just have a look. So here, we want to get the basically 97.5% quantile of the t distribution with the number of the degree of freedom 96. So it is Qt 0.975 and 96. So you should get this number 1.98. So I will copy this number here, and also I will just copy the code Qt 97596 equals to 1.9850. So by using R, you can use this Qt function to get the quantile. So it returns the, what's the meaning for this? So it just means the 97.5% quantile of t distribution with the degree of freedom 96. So in this case, you can use R to obtain this value. And also by using this table, you can get beta 3 hat and also the standard error of beta 3 hat. So in this case, if I just give you this R output, and also I just give you the R output of this Qt function, you should get the confidence interval for beta 3. So I think usually in final exam, I just give you this R output, and also I just give you the R output for the for this Qt function result. And then you need to find the correct value of beta 3 hat, and also standard error of beta 3 hat, and also the correct value for the number of the degree of freedom. So the number of the degree of freedom here is at this position of this table. So any questions about how to use our output to compute the confidence interval? And this is about the confidence interval of single coefficient beta j. So let's look at the confidence interval for more complicated case. So what's the confidence interval for this mean of response? So what's the mean of response? So that is the mean of y given values of x1 equals to x10 until xk equals to xk0. So because we have the multiple linear regression model, so that means the mean of response here is actually this linear combination. So this is exactly our mean of response. So what is the confidence interval for this mean of response? And another question is what's the prediction interval for y new for our response variable at some new explanatory variable values? So in order to answer these two questions, we need to firstly prepare this 1 minus alpha divided by 2 quantile for the t distribution. So if we have this quantile, just like what I have done by using R, we can prepare this quantile. And then we can give this prediction interval and also confidence interval. So how can we do that? So I just compile these two, I think, in one page because I think it's easier to get confused by those two. But I think the very important distinction for these two is actually from the target, because they have totally different targets. The first one is just to get the confidence interval for the linear combination, or in other words, the mean of response. The second one is actually to predict y new, which is a random variable. So in order to estimate this linear combination, the best single estimation is just to consider this by using this plugin idea and consider this linear combination by plugging in those estimates. And also the confidence interval is just to consider the estimation of the linear combination minus plus the quantile times the standard error. So this idea is very similar if you still remember the idea here. The estimation minus plus quantile times the standard error. But for the prediction interval, because we have a totally different target, we have y new, and y new just equals to the beta 0 plus beta 1 x1 plus so on and so forth until beta k xk. And the most important thing here, we actually have this extra term, epsilon nu. And epsilon nu follows a normal distribution with mean 0 and the standard variance sigma square. So for this y new, the best single prediction is just to consider the first part and also plugging in the estimates. So that's the single prediction. And in order to get the prediction interval, so what you need to do here is just to consider the single prediction minus plus the quantile, and then we need to modify the standard error a little bit by considering the variation of epsilon nu, because the variation of the epsilon nu here just can be captured by using this sigma square. So that's the standard deviation or the variance of epsilon nu. So what you need to do here is just to involve this sigma square into the expression of the prediction interval. So you need to involve the variation because we want to predict y, and also the variation of the epsilon nu should also be involved in the expression of the prediction of y. So here we have this extra sigma hat square. And then just plus the standard error of this, the squared standard error of this linear combination. So that's the difference between the prediction and also the confidence interval. I think the most important distinction is the targets are totally different, so we have different results. And here, there is a question that what's the standard error for this linear combination of the estimates? And the answer is that we do not provide in this course because it is more involved by using the linear algebra notations. And this course is not a math course, and we do not require you to understand a lot of the linear algebra, just very basic, I think is enough. So in this case, I will not require you to compute the standard error of this linear combination, but you do need to understand the difference between the prediction interval and also the confidence interval by using this expression. I think it's much more clear. So I think later I'm going to use the real example, and then I'm going to use the R code to compute the prediction interval and also the confidence interval. So if you still remember how to use R code to compute the prediction interval and the confidence interval in the simple linear regression model case, you will find that there is not much difference. And if you still remember, in order to compute the confidence interval, what you need to do here is just to use this confidence argument. You need to specify the interval here is the confidence interval, and then R will return the confidence interval. And if you specify prediction interval, and then R will return prediction interval. But even if we want to get the confidence interval, we always use this predict function. So it's just a function, but it can return the confidence interval if you specify the interval equals to confidence. So if you want to get confidence interval, just input confidence. If you want to get prediction interval, just input prediction. But you always use this predict function to get those two. So that's how we can use R to obtain the prediction interval and the confidence interval. And I will explain more details, just to give you a very straightforward look at it. So in order to explain all the inferential tools in this course, not in this course, actually in the multiple linear regression model, we are going to use this data set to predict the brain weight. So this is our response variable. And what are the other explanatory variables? We have the litter size, we have the gestation period, so this is the meaning for the gestation period, and also we have the body weight. So the reason why we want to predict the brain weight is that it's really hard to observe. We can actually observe the litter size, we can observe the gestation period, we can also observe body weight. It's easy to get the body weight, but it's really hard to get the brain weight, especially for live animals. For instance, you cannot cut the head of a monkey in half because it's cruel and it's not animal protecting. But if you can observe the litter size, gestation period, body weight of a monkey, maybe you can use this data set to predict the brain weight of a monkey. So that's the reason why we consider this data set to predict something which is hard to, some data which are hard to get, for instance, like this brain weight. So here we have these 4 variables for different species of mammals. We have different species of mammals. And how can we get this data? And a lot of students, when I do not upload data on the Wattle, a lot of students just ask me, how can I get the data? So basically, when I do not upload the data on Wattle, so that means the data is contained in some object in the R package. So that just means that our data have been saved in object case 0902. So in order to call this data, just to use this case 0902 directly. But before that, you need to install the packages sleuth3. So that means this data set is only included in this data set, in this package sleuth3, and then use library sleuth3 to call this library. So I think that's the second time for us to use the data set in our textbook. So when we use the data set in our textbook, I think it's much easier. What you need to do here is just to install the package and then load the package and just call the name of the data set. So here, the name of the data set is case 0902. So what you need to do here is just to use this object directly, so that will give you the data set in the lectures. You do not need to download any CSV file to get the data. I think that's the second time. So maybe I will explain it for the third time. So in this data set, firstly, let's just have a look at what's inside this data set by using this names function. This names function basically gives the, I think, the column names of this data set. So in this data set, we have the different variables. We have species, brain weight, body size or body weight, I think, body weight, and gestation period, and also litter size. So we have like 5 variables. I think also you can see the variable explanation in this page. And in order to get the roughly idea about the relationship between different variables, we consider to use this scatter plot matrix. So in order to get this scatter plot matrix, we need to use this pairs function. So that returns the scatter plot matrix. And for this scatter plot matrix, in order to do that, we actually eliminate the species because it's the categorical variable. So we usually consider to use the scatter plot matrix for usually only for the continuous variable. So how can we eliminate one variable in the data? Just to use this square bracket -1. So that just means we eliminate the species variable. So that means we only have these 4 variables left, and then we just draw this scatter plot matrix. So this is the scatter plot matrix. So how can we look at this scatter plot matrix? So what you need to do here is just to put brain here. So that means the y-axis in this plot here is brain. And then you can put body here. So that means the x-axis here is the body weight. So in this 2, 1's element of this scatter plot matrix, not 2, 1, it's 1, 2, sorry. It's 1, 2's element of this scatter plot matrix. You can have the scatter plot of brain and versus scatter plot of brain versus body weight. And similarly, you can know how to observe, how to explain the other plots in this scatter plot matrix. I think it's very similar. So firstly, I think our impression for this plot is that maybe we cannot use the linear regression, because if we look at because we want to predict the brain, so basically we need to put brain on the y-axis, and if we have a look at it, so it's really hard to find a linear line here to fit the data by using the other 3 variables. So let's consider some parameter transformation. So here we consider the parameter transformation by considering this logarithm transformation. And a student asked me this question about what's the meaning for this log here. So here, this log just means log e. It does not mean log 10. Please be careful about here. So in R and also in this course, we always consider log e, not log 10. So if we consider this log transformation, we should get all the log of the variables. And because we want to predict the brain weight, so we just put brain weight as y. And then we can have a look at the relationship between brain and also the other variables. So if we have this transformation, the brain weight basically has this kind of linear shape with the log of the body weight. And also, the relationship between log bring and log gestation is also kind of linear. But for this liter size, so it's really hard for us to use a regression line to fit it. But we can just have a try, and then we can consider to use the hypothesis testing to get our result, whether or not we have a linear relationship between the log bring and also log liter size. So that's how we use this scatter plot matrix. Any questions? So the next thing here is just to construct the response variable. We want to predict the bring weight. And we put three variables, x1, x2, x3. x1 is the log of the gestation period. x2 is the body weight. x3 is the liter size. Then what we can do here is just to use this LM function. I think that's standard. And then we use this summary result to get all of those estimates. So we can have the estimates beta 0 hat, beta 1 hat, beta 2 hat, beta 3 hat here. And also we can have all the hypothesis testing. So it seems that all the hypothesis testing result for the t-test here, this only gives you the hypothesis testing of the t-test, are significant. But remember that the significance for the t-test actually depends on the other variables. So in this case, we need to use the f-test to help us to understand some, or to answer some questions. So what's our question? If you still remember, I think in the beginning, because I didn't mention it, but you may have a look at the slides, and I will not read the slides exactly. So the question here is that after accounting for the body weight, whether or not we have more variables to be associated with the bring weight. So that's our question. So we have already known that the body weight has something to do with the bring weight. So we just want to know, instead of the body weight, do we have more variables which can be used to predict the bring weight? So that's our question. So here we have x2. x2 is the body weight. So that means, firstly, we have already known x2 is going to be very useful. So we have already put it in the model. So what we care about here is that we care about whether either of x1 and x3 or both are important to predict y. So usually if we have this kind of question, we should consider this f-test. So what's the meaning for this f-test? That just means, firstly, beta 1 equals to beta 3 equals to 0. So that just means that if x2 is included in the model, x1 and x3 are not needed. So that's the meaning of the non-hypothesis. So the meaning of the alternative hypothesis is that if x2 is already included in the model, x1 and x3 are at least one of these two variables are needed. So that just means at least one of x1 and x3 is needed. So that's the meaning for this hypothesis testing. So in order to perform this test, firstly, we need to know what's the full model, what's the reduced model. So the full model is just the model with all the variables. So we just save the full model result in this bring.reg, bring.regression object. So that's our full model with all the explanatory variables. So what's the reduced model? Because here we have beta 1 equals to beta 3 equals to 0 as the null hypothesis. So the reduced model should be the model which only includes x true in the regression. So here, the reduced model here is just the bring.regr, and we just save the reduced model result in here, in this object. So remember, the idea for the f-test is just to compare the difference between the reduced model and also the full model. So what you need to do here is just to use this ANOVA function to input the reduced model and also the full model, and then you need to specify its f-test. Then you can get the f-test result. So what's the f-test result? This table gives you the f-test result. So this f here is just the test statistic of f-test. And also you have this p-value, corresponding p-value. So how to interpret this result? So basically this p-value is really small, so that means we reject the null hypothesis and get the conclusion that if x true, so that's the body weight, is included in the model, then at least one of x1 and x3 is needed in the model. So that's the conclusion for the f-test. We can get this conclusion, at least one of x1 and x3 is needed in the model. So any questions about how we use R to get the result for the hypothesis testing? So we can also get this testing of overall significance. So that means we can test all the regression coefficients except for the intercept. And in this case, the reduced model here is 1. So what's the meaning for 1? So that means we remove all x1, x2, x3. So that's the reduced model. And the next step is just to use this ANOVA function to compare the difference between the reduced model and also the full model, and then you can get the result. So this is the f statistic, and this is the p-value. So by using this p-value, we can get this conclusion that we reject the null hypothesis. So that just means the alternative hypothesis is correct. So what's the meaning for the alternative hypothesis? So the alternative hypothesis just means at least one of these three variables is needed in this multiple linear regression model. So that's how we use this ANOVA function to get the result for the overall testing of overall significance. But this result is actually here in the summary output. So where is it? So remember here, the F statistic here is 631.6, and also the p-value is really small. So if you have a look at this table, if you look at the last row, here, this is the F-test statistic of beta 1 equals to beta 2 equals to beta 3 equals to 0. And you can find that this value is exactly the same by using the ANOVA function in the following page. And also we can have the corresponding p-value. Besides, we can also have the number of the degree of freedom for this f-test. So if you still remember, this f-test should be compared to the f distribution. So what's the f distribution? The f distribution is fd n minus k minus 1. So that means in this testing of overall significance, d just equals to 3, and n minus k minus 1 equals to 92. So that means here, this 92, and also here we have another 92. These two both give us the result for the number of the degree of freedom, but here you need to be very careful that this is the R output for the full model. So by using this R output for the full model, we can get the F statistic and also the corresponding p-value, and also the number of the degrees of freedom of the F distribution by using this R output, but only for this testing overall significance. We do not have the other F-test result. We only have this one situation. So that means this result is also in page 30. So you need to compare this result to page 30. So that's the testing of overall significance. And another special case of the F-test is just to test a single coefficient. And still, by doing that, you need to know what's the reduced model. So the reduced model here, because beta 3 equals to 0, so that means the reduced model is this model by removing x3. And then what you need to do here is just to use this ANOVA function again, and then you can get this F statistic and also this p-value. So remember that this F-test is a special case of the F-test, and also it is equivalent to t-test of beta 3 equals to 0. So what you can do here is just to compare this p-value to the p-value in page 30. So here, the p-value here is 0.0088. And if you compare this p-value to this p-value in page 30, you can find that those two p-values are exactly the same. So that means we can use different methods to test the beta 3 or one coefficient equals to 0. We can use the t-test method, or we can use the F-test method. But they give exactly the same result. So that's how we use the R to accomplish the hypothesis testing. Any questions? These are really important. So I think at the end, let's just look at how to use R to get the confidence interval and also the prediction interval. So for the confidence interval, I think you have already known to use this predict function, so I will not repeat it. And also, you need to put the confidence level. So here, 95% here just equals to 1 minus alpha. So when we talk about 1 minus alpha confidence interval, we usually consider 95% confidence interval. And I think what's the most important thing here is this x0. What's this x0? You need to be very careful here, because I think during your assignment 1, some students will definitely ask this question, why their predict function does not work to obtain the confidence interval and prediction interval. The reason is usually from this definition of this x0. So the x0 is a data frame consisting of the values of x1, x2, and x3. So you need to be careful such that those are just the names. Variable names should be the same as when you use LM function y tilde x1 plus x2 plus x3. So you need to have the exact column names, the variable names. Otherwise, you will never get the correct prediction result. Please be very careful about it here. And also, you need to know that it's a data frame. It's actually not a vector or not a matrix. It's a data frame. And then you can input this x0 here, and then you can obtain the mean, the prediction, the confidence interval of this mean of response. And for the prediction interval, we actually predict y nu. And we predict y nu equals to, in this case, it is beta 0 plus beta 1 x1 nu plus beta 2 x2 nu plus beta 3 x3 nu plus epsilon nu. we are predicting this. So we need to input the new value of x1, x2, and x3. So similarly, you need to get this data frame, which has the exact same variable names as this LM function. Otherwise, you will never get the correct prediction or confidence interval result. So any questions about these inferential tools? So I think even though I think at last I use not a lot of time to talk about the R output, but still you need to spend more time when you're at home, I think maybe in your tutorials to practice those R code. And if you have any questions, I'm really happy to help you during my consultation hours. No question? Okay. Now let's just take, even though it's quite close to the end of today's lecture, but I still plan to release you. So just to take a 1 minute break, and then we are going to talk about a little bit start of this new topic, model diagnostic tool, model diagnostics for linear regression tool, because the R square is highly related to the sum of the squared error. Okay, let's use this last 5 minutes to briefly talk about what's the meaning for the R square and sum of the squared error. So for the sum of the squared error, we just talked about it today, so you should be very familiar. So the sum of the squared error, literally from its name, is just the sum of the squared error. And if you do attend your tutorial 2 or try the tutorial 2 problem set, you will find that actually you can compute the sample variance of the residuals. So if you have you can compute the residual I, and then you can compute the sample variance of the residuals. The result should be in this formula. So that is, for the simple linear regression model, it's exactly equal to the sum of the squared error divided by n minus 1. So it's only for, I think in tutorial 2, it's only for simple linear regression model. But actually, this is also true for the multiple linear regression model. And remember that because it's a sample variance, so that means it can be used to measure the variation in residuals. And in other words, because the sum of the squared error only has this constant difference compared to the sample variance of the residuals, so that means sum of the squared error can also be used to measure the variation in the residuals. So that's the interpretation. Another interpretation for the sum of the squared error. The sum of the squared error can be used to measure the goodness of fit for the multiple linear regression model, and also the sum of the squared error can be used to measure the variation in the residuals. So that's the other interpretation of the sum of the squared error. And similarly, we can use the sample variance of y, so this is the sample variance of y, to measure the variation in the response variable. And if we consider this SST, so the only difference between the SST and also the sample variance is this constant 1 divided by n minus 1. So in this case, this is called the total sum of squares, SST, can also be used to measure the variation of the response variable. So here, we have the sum of the squared error to measure the variation in the residual, and also we have SST to measure the variation in the response variable. And similarly, we can measure the variation in the fitted value. So the variation in the fitted, what's the variation in the fitted value? It's exactly this sample variance of the fitted value. And also, in tutorial 2, we have shown this result for the variation for this sample variance of the fitted value. And also, this result is also true for the multiple linear regression model. So in this case, we can define another thing, which is called sum of the squares due to regression, which can be represented by using this SSR. So the SSR is just we only have this scalar difference between the sample variance and also SSR. So SSR can also be used to measure the variation in the fitted value. So we have the variation in the response variable and also the variation in the response variable. This is the variation in the response variable. This is the variation in the residual. And lastly, we have the variation in the fitted value. So we need to have a look at the relationship between these variations. So what's the relationship here? So if we derive this sum of the SST, so that's the variation in the response variable. So by using some formula, we can just minus fitted value yi hat and plus fitted value yi hat. And intuitively, we can split this summation into two parts. You can find that the first part is exactly the sum of the squared error, because the difference here is the residual I. And the second part is this sum of the is this SSR, sum of the squares in due to regression. So in this case, we have this equation, we have this decomposition for the variation in the response. So by using the regression model, we can have this result that the variation in the response can be interpreted by using the variation in the residuals and also the variation by using the fitted values in the regression. So that means we actually, in the regression model, we want to use this variation in the fitted value to explain the variation in the response. So I think that is the end of today's lecture. And I'm going to talk more about the sum of the squared error